Welcome back to the deep dive. I was looking at the stack of papers we have for today, and it really hit me. Usually, when we talk about ADHD or attention deficit hyperactivity disorder, the conversation is, well, it's entirely surface level. We talk about the behavior.
We talk about the checklist.
Exactly. The checklist. You fidget, you lose your car keys,
Yeah.
you interrupt people in meetings, you have that general sense of chaos following you around.
Right.
And if you go to a doctor, that's what they ask you about. They ask about the result of the condition.
Of course. They ask about the external symptoms because that's what impacts your life and, the lives of the people around you. It's the visible part of the iceberg.
But today, we are doing something completely different. We are pushing that behavioral checklist to the side. We aren't asking what does ADHD look like. We're asking what is ADHD. We are going directly to the source. We're going into the physical wiring of the brain itself.
Which is really where the conversation needs to be if you want to actually understand the why behind the what. If you want to move past the stigma, you just have to look at the biology.
So to do that, we have pulled a massive stack of neuroimaging literature. And I want to be really clear to you listening, this isn't the pop psychology stuff you see on social media.
No, not at all.
We're talking about the heavy hitters. We're talking about seminal reviews, meta-analyses of hundreds of fMRI studies, and some really, really cutting-edge papers that just came out.
It is a heavy stack, and frankly, it's a necessary one. Because the science has moved so fast in the last, 10, 15 years, it's incredible. We're going to be leaning very heavily on the work of some, titans in the field.
So who are we looking at?
We have the foundational work from Amy Arnsten at Yale, particularly her 2010 paper, The Emerging Neurobiology of Attention Deficit Hyperactivity Disorder. It really set the stage.
And I see a lot from Katya Rubia here.
Yes, Katya Rubia is absolutely essential. She's at King's College London, and she has done these massive, and I mean massive, meta-analyses spanning from 2011 all the way up to 2020, where she looks at functional imaging.
So she's taking hundreds of different studies and kind of mashing them together to find the common thread.
That's it, exactly. Seeing what the common denominators are across all this research. And then to cap it all off, to make sure we are right on the cutting edge, we have the 2024 Nature Reviews Disease Primer led by Stephen Farrow.
That Farrow 1 paper, that's essentially the state of the union for ADHD research right now, isn't it?
It really is. It's the consensus document. It's what everyone in the field is looking to. So our mission today is to take all of this density, these thousands of pages of academic text, and construct a map.
A map of the ADHD brain.
A comprehensive map of the ADHD brain for you. We want to explain the structural changes, what physically looks different. We want to explain the functional glitches, which parts aren't firing when they should. And maybe most importantly, we want to talk about the connectivity issues.
And that leads me to the big question, the hook for this whole deep dive. Because I think a lot of people, even those who have a diagnosis, have this lingering doubt. When you look at all this data, is the ADHD brain actually built differently? Like, is the hardware different? Or is it just functioning differently, like a software bug, where the computer is fine, but the program is just glitchy?
That is the million-dollar question. It's the question that really determines whether people see this as a discipline problem or a biological one. And the answer, which we are going to unpack today, is that it's absolutely both.
Okay.
The hardware is different and the software is different. But there's a third factor that might be even more critical, and that is connectivity.
Connectivity. So you mean how the different parts of the brain talk to each other?
Precisely. It's not just that specific parts of the brain might be slightly smaller or maybe less active. It's that they aren't talking to each other effectively. It's a network failure. Specifically, as we're going to see, it's about how the brain struggles to switch gears.
It gets stuck?
It gets stuck.
Okay, stuck is a word I think a lot of our listeners with ADHD, or who know someone with it, will feel in their bones, that feeling of paralysis. So let's peel this back layer by layer. Let's start with the hardware, the actual architecture of the brain. If I take an ADHD brain and put it next to a neurotypical brain in a lab, what are the structural differences I'm seeing?
So if we start at the top, or maybe more accurately at the front, we have to talk about the prefrontal cortex. The PFC.
The CEO of the brain. Everyone always calls it the CEO.
It's a cliche, I know, but it really fits. This is the newest part of the brain, evolutionarily speaking. It sits right behind your forehead. It's responsible for all that high-level management.
So planning, decision-making.
Regulating attention, behavior, emotion, planning for the future, all of it. And in that 2010 paper by Amy Arnsten, the one published in the Journal of Pediatrics, she lays this out very, very clearly. She states, and this is a critical finding, that ADHD is associated with weaker function and structure of prefrontal cortex circuits, especially in the right hemisphere.
Okay, let's pause right there. Especially in the right hemisphere. Why does the side matter? I kind of thought the brain was just the brain.
Not at all. The brain is highly lateralized. Different sides, different jobs. Arnsten's work, and a lot of work since, points out that the right hemisphere of the PFC is specialized for a very, very specific task. Behavioral inhibition.
Inhibition. So the ability to stop, to put on the brakes.
Exactly that. The ability to stop an inappropriate response, to not say the rude thing you're thinking, to not stand up when you're supposed to be sitting down, to not click buy now on the website when you know you shouldn't.
So it really is the brakes.
It is the brakes. And if the structure and function of that right PFC are weaker, if you physically have less gray matter there, or maybe the connections are thinner, you literally have a weaker set of brakes.
That's terrifying and honestly validating at the same time. Because if I'm driving a car and the brake pads are thin, it doesn't matter how good of a driver I want to be. I'm going to slide into that intersection.
That is the perfect analogy. You can want to stop. You can know you should stop. But the mechanical lever that executes the stop command is faulty. It's a hardware problem, not a willpower problem.
But it's got to be more than just the PFC, right? The cortex is the outer layer, the wrinkly part we all recognize. But ADHD doesn't feel like a surface-level issue.
No, it's not. Not at all. For the next piece of the map, we need to go deeper into these subcortical structures, the parts buried deep inside the brain, the sort of ancient brain.
The lizard brain.
Well, more the mammalian brain. And here we need to talk about the basal ganglia.
Okay, the basal ganglia. I always hear this associated with movement, like Parkinson's disease involves the basal ganglia, right?
It is about movement, yes, but it's also about habit formation, motor control, reward processing. It's a major hub. And there's a really significant paper on this published in 2020 in Psychological Medicine by Lucido and colleagues.
What was so significant about it?
It wasn't just one study. This was a comparative meta-analysis of brain structural abnormalities across thousands and thousands of patients. They were pooling data from all over the world.
So they're getting a really clear picture. And what do they find down there in the basement of the brain?
They found reduced gray matter volume.
So literally less brain tissue.
In specific areas, yes. They found reduced gray matter volume in the basal ganglia, which, makes sense given the hyperactivity, the fidgeting, the restlessness.
Sure.
But, and this is key, this is where it gets really interesting, they also found it in the amygdala and the hippocampus.
Whoa, wait a second. Amygdala and hippocampus, those are famous regions. The amygdala is the fear center, the emotion center. And the hippocampus is all about memory.
Exactly. And this is where our map starts to get really interesting and where we start to move away from ADHD just being about attention. If you have a structural reduction, less gray matter in the amygdala and hippocampus, it suggests that ADHD is not just a disorder of focus in the academic sense.
So what is it then?
It implies a fundamental issue with emotional regulation and how we learn from the past.
That explains so much. If the hippocampus, the part that records context and memory, is structurally different, maybe that's why it's so hard to learn from mistakes. You make the same error over and over.
Right. Think about how a child learns not to touch a hot stove. You touch it, it hurts. The amygdala records the emotion fear, pain, and the hippocampus records the context stove equals pain. Next time you see the stove, and that whole memory circuit triggers a warning.
But in ADHD,
if those structures are smaller or less robustly connected, that loop is weaker. You might touch the stove again. Or, more realistically in adult life, you make the same social mistake again. Or you procrastinate on a project again, even though you know for a fact it caused you immense stress last time.
the pain of the past doesn't inform the present as strongly.
It doesn't have the same weight. And the amygdala involvement you mentioned, that speaks directly to that intense emotional dysregulation that so many people with ADHD report. Things like rejection-sensitive dysphoria, for example. The sudden floods of emotion. It's not just, I can't focus, it's, I feel things overwhelmingly.
And the regulator for those big emotions is physically smaller.
Potentially, yes. The volume is reduced. It's like having a smaller container for a huge amount of emotional water. It's going to overflow.
So we have a smaller right prefrontal cortex, meaning bad brakes.
Yeah.
And we have reduced volume in these deep emotional and motor centers, which means no emotional rudder.
That sounds, well, to be blunt, it sounds like damage. Is the ADHD brain damaged?
I'm really glad you asked that because damage is such a loaded word and it's inaccurate. It implies something was whole and then it got broken. The literature actually points to a much better word, delayed.
Delayed. Yes. And this brings us to what's called the maturational delay theory. There's a seminal paper that's cited in almost every major review, including the Farron 2024 primer. It's from the Proceedings of the National Academy of Sciences, or PNAS, by Shaw and his colleagues way back in 2007. It is still the gold standard for understanding this structural piece.
Okay, so what did Shaw discover? Walk us through that study.
So Shaw and his team at the National Institutes of Health did something brilliant. They didn't just take one picture of the brain. They followed hundreds of kids over many years, taking brain scans repeatedly. They were tracking something called cortical thickening.
Cortical thickening, what is that? Sounds like the brain is getting fatter.
Sort of. As a child grows, the cortex, that outer layer, gets thicker and thicker as new neural connections are built. It's like a forest growing dense with trees and undergrowth. But then, at a certain point, it hits a peak and starts to thin out.
Thin out, that
Yeah.
sounds bad.
No, it's actually a very good thing. It's a process called pruning. The brain essentially says, okay, we've got way too many connections here, it's inefficient, let's cut the ones we aren't using and make the important highways faster and wider. So, maturity is defined by hitting that peak thickness and then starting the pruning process.
Okay, so you build up this big block of marble, and then you start carving away the excess to make the statue.
That's a perfect analogy. Now, what Shaw found was that in neurotypical children, this peak thickness, the moment they stop building and start carving, happens around age 7 or 8.
And in the kids with ADHD,
The peak didn't happen until age 10 and a half.
that's a 3.5-year difference.
In the prefrontal cortex, yes, that is a massive chronological gap in development. Imagine a 5th grade classroom. You have neurotypical kids whose brains are already carving the statue. They're refining their impulse control, their organization. And sitting right next to them is a child with ADHD whose brain is still just piling on the clay.
So you have a 10-year-old child who literally has the prefrontal cortex maturity of a 7-year-old.
Precisely. And this is why the Shaw paper was so important. It explicitly states, and I'm quoting the title here, attention deficit hyperactivity disorder is characterized by a delay in cortical maturation. It's not a deviation. The brain isn't growing in some weird alien pattern. It's following the exact same developmental pattern, just shifted in time.
That puts a completely different spin on behavior. If you're asking a 12-year-old to organize their schoolwork like a typical 12-year-old, but their biological hardware for organization is at the level of a 9-year-old.
Then you are setting them up for failure and frustration. It's not that they won't do it, it's that the machinery to do it reliably isn't online yet. You wouldn't get mad at a 7-year-old for not being able to drive a car. Their feet don't reach the pedals.
You know, that's actually incredibly hopeful, though, because a delay implies you might eventually catch up.
In many cases, yes. The study showed that eventually, the ADHD brains did hit that peak and start the pruning process. It just happened later. This helps explain why some people seem to grow out of the worst of the hyperactive symptoms, or at least why things tend to stabilize in their mid-20s.
The hardware finally arrives.
The hardware finally comes online.
Okay, so that's the hardware. We've got some smaller components, some delayed components, particularly in the control centers. Now let's talk about the software. When you fire up this delayed computer, how does it run? What's happening functionally?
This brings us to functional activation. So now we're moving from MRI, which gives you pictures of structure, to fMRI, which gives you videos of blood flow. We're watching the brain in action. And to really understand this, we need to divide the brain's software into 2 main categories: cool executive functions and hot executive functions.
Oh, and hot. I like that. Break it down for me.
Cool. Executive functions are what you use for logic, for planning, for working memory. It's the dry, non-emotional, cognitive stuff. Sitting down to do a math problem, deciding which email to answer first, organizing a file cabinet.
And hot is?
Hot is all about motivation, reward, emotion. It's the system that you use when you're deciding if you want to eat that piece of cake or wait for dinner. It's the system that handles desire and immediate gratification.
Got it. So logic versus desire. Let's look at the cool functions first. What happens in an ADHD brain when it tries to do a math problem or focus on a boring spreadsheet?
For this, we have to look at a major review by Katya Rubia, the one published in Frontiers in Human Neuroscience in 2018. She synthesizes a massive amount of data here, and the pattern is clear. When people with ADHD perform these cool inhibition or attention tasks inside a scanner, we see significant underactivation.
Underactivation, so the brain isn't working as hard as it should be.
Or rather, the specific areas that should be working aren't getting enough blood flow. The lights just aren't coming on as brightly. Rubia's meta-analysis points to three specific areas that are consistently underactive: the inferior frontal cortex, IFC, the anterior cingulate cortex, ACC, and the supplementary motor area, SMA.
Okay, let's unpack those acronyms because otherwise they're just alphabet soup. Start with the inferior frontal cortex, the IFC. What does that do?
You had talked about the brakes earlier.
Yes, the PFC.
The IFC is the brake pedal itself, specifically the right IFC. When you need to stop an action like you start to reach for your phone, but then you remember you're in a meeting, your right IFC is supposed to light up bright red on the scan and shout, "No!"
It's the stop signal.
It's the primary stop signal for motor actions. And in ADHD,
It's dim.
it's dim, it's underactive, it's like stepping on a brake pedal that is spongy. You press it, you have the intention to stop, but the hydraulic pressure just isn't there. The car keeps rolling forward a few more feet.
I love that spongy brake analogy because it removes the morality from it. It's not that the driver's a bad person, the pedal is soft. So what about the next one? The ACC.
The anterior cingulate cortex. Think of this as the brain's uh-oh monitor.
Yeah, well, monitor.
It's your internal conflict monitor. It sits right in the middle of the brain, and it constantly scans for errors or mismatches between your intention and your action. If you're typing a sentence and you accidentally hit the wrong key, the ACC lights up for a split second and says, "Whoops, that's not right. Fix that."
And in ADHD, the uh-oh monitor is broken. Asleep at the wheel.
Asleep at the wheel is a great way to put it. Rubia's work shows it is significantly underactive. So not only do you have spongy brakes with the AFC, but you also might not even realize you're about to crash until it's too late because the conflict monitor, the ACC, didn't alert you to the mistake.
That explains that feeling of carelessness. You know, when you make a mistake and someone says, "How did you not see that?" I mean, you honestly have to answer, "I don't know."
Yeah.
Your brain literally did not signal the error properly.
Exactly. It's a failure of the internal monitoring system, a glitch in the software that's supposed to catch bugs.
Now, you mentioned a third functional deficit in the outline that I found really, really surprising. We talk about inhibition all the time, but we rarely talk about timing.
Oh, this is a huge one, and it's so often overlooked in the popular conversation about ADHD.
Timing, you mean like rhythm, like being a bad dancer?
I mean the brain's internal clock, the ability to estimate how much time has passed or to predict when something is going to happen in the near future. There's a meta-analysis specifically on this by Hart and his colleagues, published in Neuroscience and Biobehavioral Reviews back in 2012.
Okay, so what do they find regarding our sense of time?
This is where the map flips a bit. While inhibition is largely a right hemisphere issue, remember, the brakes timing deficits often show up as left hemisphere dysfunction.
Interesting.
Specifically, the left inferior prefrontal cortex and, this is the kicker, the right cerebellum.
The cerebellum. I thought that was just for balance, you know, making sure I don't fall over when I walk.
That's the old view. That's what we all learned in high school biology. We used to think the cerebellum was just for motor coordination. But we now know the cerebellum is a master processor for temporal prediction. It helps the brain predict when a sensory event is going to happen.
So if your cerebellum is underactive,
You are literally out of sync with the world. Your internal metronome is off.
can you give me a real-world example of what that feels like?
Sure. Imagine you have an appointment at 2:00 p.m. It is currently 1:00 p.m. To a neurotypical brain, the cerebellum and the left PFC work together to give you a feeling of that hour. You can feel the weight and shape of it. You know you have enough time to wash the dishes, maybe check the mail, and then leave at 1:45.
Right. You can sense the container of time.
But in ADHD, that temporal prediction network is offline. The concept of 1 hour is just an abstract number. It has no feeling. It could be 5 minutes. It could be a whole day. So what happens?
I can guess.
You either get time blindness, where you start washing the dishes and you look up and suddenly it's 2:15 p.m. and you're late. Or you go into what many people call waiting mode. You sit on the couch, paralyzed, doing absolutely nothing for that hour because your brain cannot accurately predict if you have enough time to start and stop another activity. You are frozen by the inability to measure time.
That is profoundly validating. Waiting mode is such a real thing. It's not laziness. It's a defense mechanism against a broken internal clock.
It is exactly that. The Hart paper highlights that the ADHD brain struggles to recruit these timing networks, so the world feels unpredictable. And when the world feels unpredictable, it causes a lot of anxiety.
Okay, so that's the cool stuff. Logic, braking, timing, The whole dashboard is basically broken. What about the hot stuff, the rewards, the emotions? This is the engine, right?
This is the engine. And this is where we get into a really cruel paradox. This is covered extensively in both the Rubia 2018 review and the brand new 2024 Farallon primer.
A paradox, how so?
Yes. When we look at the brain's reward system, specifically the ventral striatum and the orbitofrontal cortex, we see two opposing things happening at the same time. First, let's talk about anticipation.
Looking forward to something good.
Right. In a neurotypical brain, if I tell you, hey, if you finish this boring report, I'll give you $100, your ventral striatum lights up immediately. You get a little hit of dopamine just thinking about the reward. That dopamine then fuels the work. It's the gas in the tank.
And in ADHD.
The ventral striatum is silent. There is reduced activation during reward anticipation.
So I tell you about the $100 and your brain just goes, meh.
Exactly. The concept of a future reward doesn't trigger the chemical release necessary to motivate the present action. So you're trying to drive the car, do the work, with no gas in the tank. This is the biological reason why future consequences don't motivate people with ADHD. You'll fail the test next week, doesn't light up the brain.
So you can't feel the future reward, which means you have no motivation to do the work now. But you said there was a paradox. What's the other side of the coin?
The other side is the outcome, the immediate moment. While the anticipation is weak, the emotional reaction to the immediate reward or the immediate punishment is hypersensitive. We see enhanced activation in limbic areas when the reward is actually delivered.
So I don't care about the cookie you're promising me for later, but if you give me the cookie right now, it is the greatest thing that has ever happened.
Or, if you take my cookie away from me right now, I will burn this house to the ground.
Right. The rejection sensitivity, the punishment sensitivity.
Precisely. The hot executive functions are dysregulated in both directions. Under-aroused by the future, but over-aroused by the present.
That is a brutal combination for trying to navigate daily life. You can't plan for tomorrow, but you are completely at the mercy of how you feel right this second.
It creates a constant emotional roller coaster. And again, it's not a personality flaw, it's a functional difference in how the ventral striatum processes dopamine signals.
So we've mapped the hardware. The structure is delayed and smaller in key areas. And we've mapped the software. The brakes are spongy, the clock is broken, the gas tank leaks. But you mentioned at the very beginning that the real key, the third factor, might be connectivity. How all these parts talk to each other.
This is the third, and I would argue the most important frontier of ADHD neuroscience. This is where the Farallon 2024 paper really plants its flag. We are shifting our focus from looking at regions, this part is broken, to looking at networks. The road between them is broken.
So it's not just about the destination, it's about the commute between cities.
That's a great way to put it. And to understand this, we have to talk about the villain of the story. Well, maybe not the villain, but certainly the main disruptor. We have to talk about the default mode network.
The DMN, I've heard of this. This is the daydreaming network, right? The one that's on when you're just spacing out.
Yes. The default mode network is a massive, sprawling network of brain regions that connects the front and back of the brain. It is most active when you are resting, when you aren't doing a specific task, when you are thinking about yourself, reflecting on the past, worrying about the future, or just zoning out completely.
Okay, so it's the me channel. It's all about my internal world.
Correct. Now, there is another set of networks in the brain called task-positive networks, like the ventral attention network or the frontoparietal network. These are the do channels. They turn on when you need to focus on the outside world on a task.
Me versus do.
And here is the golden rule of a neurotypical brain. These two networks are anti-correlated.
Anti-correlated, meaning what?
Meaning they act like a seesaw. When the task-positive network goes UP, when you focus, the default mode network must go down. It has to shut up. You cannot effectively focus on a math problem and daydream about your upcoming vacation at the same time. The brain physically suppresses the DMN to allow the task network to work without interference.
Okay, that makes perfect sense. One goes on, the other goes off. And in ADHD,
the seesaw is broken.
Broken how?
We can look at a huge meta-analysis by Cortese and his colleagues, published in the American Journal of Psychiatry back in 2012. They analyzed 55 different fMRI studies, a huge data set, and they found a consistent, reliable pattern of poor deactivation of the DMN.
Poor deactivation. So when I try to work, my daydreaming network just stays on.
It stays active. It refuses to shut up. The seesaw is flat. You're trying to lift the task side up, but the daydream side is still weighing it down.
So you have an intrusion.
That is the specific word the researchers use. DM intrusion. The internal world, your daydreams and worries, intrudes upon your attempt to focus on the external task.
That is the most perfect explanation for brain fog I have ever heard. Or that feeling of fighting your own brain just to read a single sentence. You read the same sentence 3 times because while your eyes are scanning the words, your DMN is screaming about what you're going to eat for lunch or that embarrassing thing you said yesterday.
Exactly. It's like trying to listen to a radio station, the task. But there is constant static from another more powerful station, the DMN bleeding through all the time.
Is this just a functional issue like a software glitch in the moment? Or is the wiring itself faulty?
It looks like it's a developmental lag in the wiring itself. There was a fascinating study by Sripada et al. In PNAS in 2014. They didn't just look at activation, they looked at the connectivity, the physical white matter tracks within these networks.
And what did they find?
They found a maturational lag, just like Shaw found with cortical thickness. The connections within the task-positive networks, like the ventral attention network, were weaker. They looked like the connections of a younger child. But more importantly, the connection between the DMN and the task networks, that crucial switch that controls the seesaw, was weak.
So the switch is loose.
The switch is loose. The brain struggles to toggle efficiently between the internal world and the external world. This explains why transitions are so agonizingly difficult for people with ADHD. Stopping a video game to go do the dishes isn't just a matter of I don't want to, it's a massive metabolic cost to force that loose, faulty switch to flip over.
And it explains the fatigue. If you have to spend all day manually holding the seesaw up, fighting that DMN because the automatic latch is broken, you're going to be completely exhausted by 2 p.m.
Cognitive fatigue is a huge part of the ADHD profile, and this DMN interference is the biological reason why.
So let's try to recap this map we've built. It's pretty comprehensive. We have a smaller, delayed hardware, particularly in the prefrontal cortex and basal ganglia. We have software that has a spongy brake pedal in the IFC and a broken clock in the cerebellum. We have a gas tank that won't hold fuel for future rewards. And now we have faulty wiring that lets the daydreaming channel bleed into the work channel because of DMN interference. It is a comprehensive map of dysfunction.
It is. But we're missing one final crucial layer. We have to talk about the chemistry that runs this whole show. Because all of these structures and networks, they run on fuel.
Neurotransmitters.
Right. And this brings us full circle back to Amy Arnstein's 2010 work. She explains precisely what the prefrontal cortex needs to function optimally. It needs a very specific chemical environment to keep that DMN suppressed and to keep those brakes working.
So what's the fuel mix?
It needs optimal levels of 2 key players, norepinephrine and dopamine. But it's not just about having them floating around. They need to stimulate very specific receptors on the neurons.
Okay, get technical for a second. Which receptors are we talking about?
Norepinephrine needs to stimulate the alpha-2A receptors, and dopamine needs to stimulate the D1 receptors in the PFC.
Why those specific ones? What do they do?
It all comes down to 2 words, signal and noise.
Signal and noise. Explain that.
Think of trying to tune an old analog radio. You want the music, the signal, to be loud and clear, and you want the static, the noise, to be as quiet as possible. Arnstein's research shows that norepinephrine acting on alpha-2A receptors increases the signal. It strengthens the relevant input. It tells the neurons, pay attention to this. This is important. It's like turning up the volume on the teacher's voice.
And dopamine?
Dopamine acting on D1 receptors decreases the noise. It dampens down all the irrelevant, distracting inputs. It tells the neurons, ignore that and that and that. It turns down the volume on the bird chirping outside the window and the sound of the air conditioner.
I see. So norepinephrine turns up the teacher, and dopamine turns down the bird.
Perfect. Now, research suggests that in ADHD, genetic changes and other factors weaken this signaling pathway. The chemical environment is suboptimal, so what happens?
The signal is weak, and the noise is loud.
Exactly. The radio is all static, the teacher's voice is faint, and the bird outside sounds like a jet engine. And this brings us inevitably to the question of medication, because this is the elephant in the room. If we introduce stimulant medications, which we know increase the available dopamine and norepinephrine, are we just masking the symptoms? Are we just artificially turning up the volume for a few hours?
Or are we actually changing the map over the long term?
This is one of the most encouraging parts of this whole deep dive. We can look at the meta-analysis by Hart et al. That we mentioned earlier, and a review by Rubia et al. From 2014 that's heavily cited in the Farallon primer. They asked this exact question. Can these functional changes be reversed or normalized?
And what was the answer?
They did something called a meta-regression analysis. It's a fancy way of comparing different groups of people within the data. They compared medication-naive patients, people with ADHD who had never taken medication, with long-term medicated patients.
What specific brain region did they look at?
They looked at the right dorsolateral prefrontal cortex, or DLPFC. This is a key area for executive control, another part of that CEO office in the brain.
And what did they find? This is fascinating.
In the medication-naive patients, just as we'd expect, this area was significantly underactive during tasks. The lights were dim. But in the patients who had been on long-term consistent medication, the activation was normal.
Wait, not just better, normal. As in, indistinguishable from the control group without ADHD.
That's what the data suggests. The finding implies that long-term treatment doesn't just mask the symptom in the moment. It may help to normalize the actual function of these specific brain regions over time.
That is profound. I think so many people carry guilt or worry that medication is a crutch or that it's harmful. But this research suggests it might be allowing the brain to function as it was designed to begin with.
It suggests that by correcting the underlying neurochemical deficit, by filling the tank with the right kind of fuel, you allow the hardware to run properly. And if you run the hardware properly over and over, day after day, it seems to strengthen the system. It's like long-term physical therapy for your brain circuits.
So let's try to bring this all together. We started with a mission to build a map. And I think we have a pretty detailed and honestly pretty staggering one now.
I think so.
If you had to summarize this entire deep dive into a few key takeaways for someone listening, what does the map of the ADHD brain look like?
I would say it's a complex interplay of three core things. First, you have structural delays. The brain, particularly the prefrontal cortex and the basal ganglia, is physically maturing on a slower timeline. It's a 7-year-old brain in a 10-year-old body.
Right.
Second, you have functional deficits. You have specific glitches in the software, a spongy brake pedal in the right IFC, and a faulty internal clock run by the left IFC and the cerebellum.
And the third?
And third, you have network interference. The fundamental wiring of the brain allows the default mode network, your internal daydreaming world, to intrude on your focus, creating that constant static of mind wandering, because the switch between internal and external is loose.
And all of this is underpinned by that chemical imbalance in signal-to-noise ratios.
Exactly. That's the environment it all operates in.
You know, for the person listening to this, the person who maybe just got diagnosed or is struggling at work or is a parent of a kid who's struggling, hearing all this can be heavy. It sounds like a lot of broken parts. My brain is delayed, my brakes are spongy, my wiring is crossed. But honestly, listening to you explain this, I don't hear a deficit model as much as I hear validation.
That is the so what of this whole deep dive. That's why this matters. If you are struggling to focus, or you say the wrong thing, or you simply cannot estimate how long a task will take, it is not because you're lazy. It is not a character flaw. It is a biological reality.
You're fighting the hardware.
You are fighting against a physical network connectivity issue. Your default mode network is literally fighting your attempt to work. Your brain's brake pedal is physically spongy.
It validates that just trying harder isn't the solution if the very mechanism for trying is what's compromised.
Right. You don't tell a car with a spongy brake pedal to just try harder to stop. You fix the brakes, or you learn to drive differently to account for them. You give yourself more following distance.
Drive differently. I love that. Before we go, I want to leave the listeners with one final provocative thought. We talked about medication normalizing brain function, but is there anything else on the horizon? Because not everyone wants to or can take medication.
This is where I want to point back to Katya Rubia's 2018 review. She dedicates a section to the concept of neuroplasticity.
The brain's ability to change and rewire itself.
Yes. The brain is not a static organ. It is constantly changing in response to experience. So the question is, if these networks are delayed, and if connectivity is malleable, what does the future hold for non-invasive treatments? Rubia races the possibility of things like neurofeedback or non-invasive brain stimulation.
So like training the brain directly, like taking your brain to the gym.
Exactly. Imagine a kid playing a video game that's connected to an EEG or an fMRI. You tell the child, okay, your job is to move this rocket ship with your mind. But the rocket ship only moves when they successfully activate their right inferior frontal cortex.
So you are gamifying the act of strengthening the brain's brake pedal.
Precisely. You are giving the brain real-time feedback and teaching it to recruit that underactive area on command. It's plausible we could eventually retrain the default mode network to switch off more reliably, rather than just using medication to boost the signal of the task network over it.
So instead of just adding more fuel with medication, we might be able to retrain the driver.
Or perhaps we can strengthen the wiring itself through targeted cognitive exercises. It's still early days for sure, but the map we've discussed today shows us where the problems are. And because we know where they are, we can start to design therapies that target them, not just with pills, but with practice and technology.
That is a fascinating and hopeful frontier. The idea that we could literally exercise our neural networks into better connectivity. Well, this has been a massive download. We hope this map helps you navigate your own brain or understand the brain of someone you love a little bit better. It's not about finding excuses, it's about finding explanations.
And once you have the right explanation, you can start building a better strategy.
Thanks for diving deep with us. We'll see you on the next one.